Okay, today we're going to be talking about logarithmic and exponential functions, actually in the reverse order. And these functions are probably, I would guess, this is an opinion, the second most important function in the BCS pool of functions, with the first being linear slash polynomial functions, then exponential logarithmic, and then finally trigonometric functions. And not that they're the only functions out there, but they are certainly the most used and the ones that you see the most often here in terms of applications. That includes combinations of these functions. Well, where do exponential functions come from? Well, we're familiar with linear functions there, in which we have a constant rate. Say that you are earning $5 an hour, or prices are going up at $5 an hour. We hope not, but let's say they do. Exponential, those are linear functions where we would say, to predict here, say we had a starting price of $8 and every hour they went up by $5. So we would have this function here to talk about after how many hours here, after X hours, after 7 hours, what would be the price? It would be the $8, the start, plus the change here. 5 times 7 would be 35. So we would have $43 for our final price. Well, that's a linear function where we have a constant amount rate of change. Exponential functions, though, are those where it's a constant percentage rate of change here. So we would be talking about prices going up by, say, not $5 per hour here, but by 5% per hour. And so let's derive here what this function would be in terms of predicting at the xth hour here, how much would the items cost. And again, let's say they start at $8 today, or right now, and we go up by 5% per hour here. So let's make a table. And we're going to have here the number of hours and the price. Or it could be the amount in the bank if you're investing at, say, 5% compounded annually, etc. So after 0 hours here, we again begin with $8 here. What happens after 1 hour here? Well, we would have our $8 and we would add 5% of $8, percent increase here. And I'm not going to be too concerned with an actual numerical answer here, but rather, as we often do in algebra, is we're more concerned about the process so that we could do the same process with very different numbers. So let's simplify this a little bit here. We have 1 times 8 plus 0.05 times 8 here. We can factor out the 8. And what we're left with here is 1.05. In other words, we have 105% of the price that we had before, 105% of 8 in this case. Well, what would happen after 2 hours? Well, we would begin here with our original price. We're going to write it like that rather than as just one number. And then we're going to add another 5% of that price that we started the second hour with. And so you can see here we have a common term, with this being 1 times it here, of 8 times 1.05. That was our common term. And what do we have? Well, we have another 105% of that. And we can see here that we can simplify that to be 8 times 1.05 to the second power. And you can see this is going to continue. After 3 hours here, well, we start with this amount for the price. And what do? We take 105% of that, and we get 8 times 1.05 to the third, and so on here. And so at the xth hour, here we would have 8 times 1.05 to the x power, because we've taken 105% x times. Now we can see somewhat of a correlation between this and linear functions, where in linear functions we started out with the rate, the original amount, and we added here, multiplying by the rate times the x here to get our y. In this case here, we again start with our original amount, but instead of adding here, we multiply, and what we see here is we get 1 plus our rate here to the x power here, 1.05. We have repeated multiplication, exponentiation here going on. And so where there was a plus before with the original amount, now we have a product, and where we had our rate before, where it was multiplication going on, we have repeated multiplication or exponentiation. So it's almost as if exponential functions there are linear functions, but ramped up one operation. So let's look at a couple of very special exponential functions, or at least one more here, is say the price or whatever we're studying, the amount of bacteria or whatnot here, doubles every hour. And it's pretty easy to see what the exponential function is going to be here, number of hours and the price. And let's say we start with $8. So we would start after 1 hour, it would be 8 times 2. After 2 hours, it would be 8 doubled twice. After 3 hours, it would be 8 doubled 3 times. Or in general, in the x case, it would be 8 times, and doubled 3 times there is 2 to the third. This would be 2 to the x power here. Doesn't really look like our previous one where we had our original amount times 1 plus r to the n power, or x power, I guess we've been writing. But if you think about it, it is going up at a constant percentage rate, because this would be 8 times 1 plus 1, easy 2, to the x power here. And what we see here is that our rate is just 100%. So when we say double there, we're saying that the price goes up by 100% rather than say something like 5% every hour. And what about a case here where we have, say, the price tripling every, not every 1 hour here, but let's say every 7 hours. What would that function look like? Well, again, we'd have the number of hours here. And what would the price be here? Well, we start with 8 at 0 hours here. And all we know that after 7 hours, or every 7 hours there, it's going to be tripling here. So we know that at 7 hours here, we're going to get 8 times 3. And after 2 times 7, or 14 hours, we're going to have 8 times 3 times 3, or 3 squared. What if we wanted to ask here, well, how much can we predict will be the price, say, after 4 hours? Well, we went from 8 times 3 to the 0 power to 8 times 3 to the first power in 7 hours here. This is 4/7 of the way. So a good guess here that this would be 8 times 3 to the 4/7 power, whatever that might mean, or at least that would lend some credence that 3 to the 4/7 power could have some meaning in that situation. And so we see here that the exponents here every 7 hours are going up at a constant rate, somewhat of a linear function here within it, just with the exponents here. And so we should expect the same thing to happen there via the hours here, is not just at the special hours like 7 and 14, but in general here we would have 8 times 3 to the x7th hours, or dollars there, for our f of x. A little side issue here, a lot of people confuse functions like x cubed versus, say, 3 to the x. And these are very different functions. And the reason is, going back to arithmetic, is when we had addition, for example, we had 5 plus 4 was the same as 4 plus 5. Or 5 times 4 was the same as 4 times 5, although this takes a little bit more to argue. But what about 5 to the 4th versus 4 to the 5th? And if you calculate these, you're going to find out that they are very different numbers here. And so while we had a commutative property of addition and a commutative property of multiplication, commutative property breaks down here at the point of what we would call repeated multiplication in terms of exponentiation. So x cubed versus 3 to the x, as a result of this arithmetic situation here, are two very, very, very different functions. And I encourage you, if you want to see the behavior of these functions here, is to set up a little table. You can do this on your TI-83 calculator. And you will see here that x equal to 0, we would have 0 cubed is 0, 3 to the 0 is 1. At x equal to 1, we'd have 1 cubed versus 3 to the first would be 3. X equal to 2, we'd have 2 cubed, which is 8. And 3 squared is 9. And they seem to be, they're different from each other, but they seem to be relatively close to each other. But if you start plugging in values, say, like 100 here, you're going to find a vast difference here between x cubed and 3 to the x. Both of them blow up, but x cubed blows up much, much slower than 3 to the x. If you graphed them, you probably could only see the graph of 3 to the x on any reasonable graph as x gets very, very big. Let's actually talk about the graph of a to the x in general here. We're going to, where a is a positive number. And you might recall here that if you plotted this graph, it would be looking like this. And we haven't talked about negative exponents or even really rational exponents here, but what happens there is, say we were looking at, say, y equal to 2 to the x here. Here we would be doubling, certainly as we go left to right here, from, say, 2 to the first to 2 squared to 2 cubed. We'd be doubling this way here, and this way here we'd be cutting in half. We'd be taking 2 to the negative 1, which turns out to be a half, 2 to the negative 2, which is 1/4, 2 to the negative 3, which is 1/8, and so on here. We would never quite reach 0 here as x tends to negative infinity, simply because we'd be taking a half of a half of a half, and if we did that, say, with a pizza, we could keep cutting that pizza in half, and every time there would still be just a little smidgen of pizza left. And so it's never going to hit the x-axis as it tends to negative infinity. It certainly blows up as x tends to positive infinity. If a is a positive number that's less than 1, the reverse happens, just for the size of the numbers here. So this would be for a bigger than 1, and this would be for a between 0 and 1. It would tend to look like this, you might recall. In looking at these graphs in another way, though, say we wanted to solve the problem here, 7 to the x is equal to 38, something like that there. Well, this would be saying here, at what x value would we get a y value, using this graph here, of 38. So we would have 38 here, and graphically, of course, we would go over here. What you can see here is this graph is a one-to-one function. So any exponential function, or at least pure exponential function, is going to be one-to-one. And that means here, well, it's always increasing, or it's down here, it's always decreasing as x goes left to right. And so that means here that it will have a pure inverse function. There is only one number here that would solve 7 to the x is equal to 38. And it turns out we give this a really weird notation from history. We're kind of stuck with it. Is this would be log base 7 of 38. And you would be thinking here is this is the exponent we would be looking at here, is what number do you raise 7 to get 38? In other words, rewriting that equation using exponentials. So that means here that we have an inverse function here, so that if f of x is equal to a to the x, its inverse function that would find the y values or would find the exponent values needed would be log base a of x. And it has its own, of course, if you look at the graph reflected about the line y equal x of a to the x here, this graph would tend to look like this. Very, very small numbers here come from very negative exponents with 7 to the x, for example, here. Very, very larger numbers come from larger x values here with 7 to the x. So we have logarithm functions are the inverse functions of exponentials there, and exponentials grow very, very big, very fast. Logarithmic functions grow very, very slow. And so what number would it take here to get, say, 343 here, very, very, sort of large number there. We would find log base 7 of 343 turns out to be a measly 3 here. So you go way out here to 343. You've only needed an exponent of 3 to get that with 7 to the x there. And so we would only be up at 3 for our y coordinate on that. Now if you recall, you also had what we called rules of exponents. Ways to do operations on exponents here and get an answer fairly, fairly quickly involving other exponents. And you also had analogous rules of logs as well. So for example, we would have here a to the x times a to the y. What is that there? Well, we say it's a to the x plus y, but why? For example, here we would have 7 to the 4th times 7 to the 5th. Well, by definition here, this would be 7 multiplied here. Actually, 3 times there. We would have 4 7s multiplied by itself. And then we would multiply 7 by itself 5 times. And combining these here, because this is all multiplication all the time, it's all multiplication here, we would have a total of 9 7s coming along there. So that kind of makes that true for natural numbers. Very easy to see that that's going to be true. By the way, if we had 7 to the 4th plus 7 to the 5th, don't go making up your own rules here, we would have the same setup as before. The only problem is we would not have this multiplication here. And so we kind of break the chain of the product there. This would be 7 to who knows at this point here. You would have to have another answer here, but it certainly would not be a whole number answer. We would also have, say, a to the x to the y power. That would be a to the xy. We would multiply it here, and again, we could see this with, say, 7 to the 4th raised to the 5th power here. We would have 7 to the 4th times 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 7 to the 4th, and we could break these up into 4 7s, 4 7s, 4 7s, or apply the rule of this from before here, and we get a total of 5 groups of 4 7s here, which turns out to be 7 to the 20th. And so that rule does make sense, at least with integer or whole number exponents. And finally, what about And maybe I should have done this secondly. A to the x over a to the y is a to the x minus y here. And again, that makes sense here. Say we had 7 to the 8th over 7 to the 3rd. By rules of, or by definition here, this is 8 sevens strung together by multiplication. And then down here we have 3 sevens strung together by multiplication. And we know in terms of canceling fractions that we cancel common factors. We have a whole plethora of common factors going on here. This 7, and this 7 here is essentially subtracting out the 3 sevens here, going like that. And so this would be 7 to the 8 minus 3, or 7 to the 5th. Well, what about non-whole number exponents? Well, first of all, what about integer exponents here? What would, say, 7 to the negative 5 mean? Well, we could use all sorts of different ways of figuring this out here. One way would be to use rules of exponents. In fact, all of these really, negative exponents, and then we're going to talk about rational and irrational exponents here, basically come from trying to make sense within the system we have involving natural number exponents and just extending that system so that those major rules of exponents still hold. So what about 7 to the negative 5? Well, this could be the answer, say, of the reverse of what we just did, 7 to the 3rd over 7 to the 8th, which is 7 to the 3 minus 8 here. So that would be what 7 to the negative 5 would mean here. By working with fractions here and canceling exponents, this would be 1 over 7 to the 5th. And so we would get that familiar rule of negative exponents here become positive exponents if we just go downstairs with the denominator. 7 to the 0 also would be a common question here, is what is 7 to the 0? There's all sorts of ways to derive this here, but we could take 7 cubed over 7 cubed by that rule of exponents. If we want it still to hold, then 7 to the 0 better be equal to a number over itself, which is equal to 1. And so any number to the 0, any positive number, I should say, to the 0 is equal to 1. Funny case of 0 to the 0 is an indeterminate form. In one case, we have 0 to a power, which should mean it's 0. In the other case, it's something to the 0, which means the answer is 1. Which one do you choose? Both of them are just as plausible, just as viable here. And actually, this could end up being anywhere in between. And you'll be studying things about indeterminate forms as we go along through the semester. What about rational exponents? Well, what about, say, x to the 1/4? What would that mean here? What we'd like to do here is say, well, what would we have? Whatever x to the 1/4 might mean, it should fit the rules of exponents. And if we take x to the 1/4 and multiply it by itself, we have 4 of them strung together by multiplication. For rules of exponents, we should be able to add those exponents and get x to the 1st power here. And so what should x to the 1/4 mean? Well, that's the number you would multiply by itself. We'll have 4 copies of it multiplied together there to give you the number. So 7 to the 1/4 is a number here that you would raise to the 4th power here to get 7. And so basically here, rational exponents here are roots. Okay, this would actually be called the 4th root of 7. What about 7 to the 5/4? Again, invoking rules of exponents, this would be that 4th root of 7 5 times. So multiply by itself. String of them, 5 of them there being multiplied. And finally, what about irrational exponents? What about 7 to the pi value here, for example? What would that mean? Well, we can't really split this up here with the rules of exponents very well with the irrational number like we could with rational numbers here. But what we could do here is we could say, hey, there's a ton of rational numbers sitting around pi that we could start finding out here. Well, what about, what about 7 to the third? 3 is very near pi. What about 7 to the 3.1? That's getting closer to pi. 7 to the 3.14. 7 to the 3.141. And we could keep going there, keep estimating pi and getting closer and closer to pi here. So it turns out how we define what the irrational number is somewhat of what we'll call a limit process there. We're going to basically say it's the limit as x gets closer and closer to pi of 7 to the x, and we can use rational numbers to try to get a picture or a feeling for what that might mean, since we already know how rational exponents, say, work with fractions and roots. Looking from the logarithm side here, we had all those rules of exponents. A to the x times a to the y is a to the x plus y. A to the x to the y, let's just look at these two here, would be equal to a to the xy here. Logarithms have analogous rules here, so if we had log base a of xy, that is, this one will be very analogous to this. Turns out to be log base a of x plus log base a of y. And what about log base a of x to the y here? That turns out to be as if you flip this over here, log base a of x, taking y copies of that here. That kind of makes sense, not even with you could derive it certainly with this rule of exponents here, but it even makes sense here, say, log base a of let's say 3 of 3 to the 5th power here. You're basically saying, what number do you raise 3 to get 3 to the 5th? It's almost like saying, what color is the green grass? We are basically treating this as the inverse function here. Log base 3, we exponentiate first, take the log, we're right back to the original place of the 5. That's a very special case of that. And because of this rules of exponents here, you can rederive this here to be not only just for things with base a, but for any x and y that it works. And so from these two rules of exponents here, you will be using these rules big time a little bit later on in something called logarithmic differentiation. But for now, it's just good to revisit an old friend. I guess I should have gone by this rule here. This is 5 log base 3 of 3. And again, what number do you raise 3 to get 3? 5 times 1, which gives you the 5. So sorry about that on that last example. And if you want, we could add in another a to the x over a to the y. It's a to the x minus y. Analogous rule of log here would be log base a of x over y here would be log base a of x minus log base a of y. So just to wrap things up there, we have log of a quotient is the difference of the logs, just like the log of the product was the sum of the logs. And that is all.